kind of, I gave it somewhere I talked about it. It was a huge display like this, but it had so much light. It was really warm. So once you close to the meter, yeah, yeah. Oh, 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 good. Thank you. Ability to say,
Okay, I guess we can start now. So let me welcome all of you uh, to today's talk by Professor Hartmut Haeffner. So Professor Haeffner has had a very distinguished career in trapped ion, various aspects of that. Uh, you might remember that he was here about a little over a year ago, and gave us a very nice talk on his work on trapped electrons. He's going to be talking about something which was a more general nature, not specifically trapped ions, for example. So, as I said, he's had a very distinguished, research career in trapped ions. So, when I first met him, he was a PhD student. That was around 2000, and he did outstanding work on the G factor of the electron. He just reminded me that it was a carbon 5 plus ion, which I think that measurement was probably a world record at that time. Maybe it still is, I guess. And so after that, he did a brief postdoc in Bangalore with us, and then moved on to the US with the Bell laureate Professor Bill Phillips, where he worked on neutral atom, cold atom. And after that, he went to Innsbruck to work on trapped ion quantum computing, Professor Rainer Blatt's group, and he was one of the guiding forces of that work. So I think it would be fair to say that he's one of the pioneers in the field of trapped ion quantum computing. If I am not wrong, there were probably two groups at that time, the NIST group led by David Weinland, and in Innsbruck led by Professor Rainer Blatt. And Hartmut's contribution to that was very, very significant. And he's written very important articles, review articles, trapped ion quantum computing, which some of you might have read. And I guess for the last 15 or 16 years, he's been at the University of California, Berkeley, continuing to work on trapped ion, including trapped ion quantum computing. And he was the director of the National Quantum Computing Center in the US, the first National Quantum Computing Center. And it's called the Challenge Institute for Quantum Computation, supported by National Science Foundation. And he continues to be there. He's a professor of physics at the University of California, Berkeley, and also an active member of the Challenge Institute for Quantum Computation. And you all know that he's also a member of our scientific advisory board, and he's given us a lot of very important ideas. And so it's really a pleasure to have him visit us again. And with these few words, I'd like to request you to give your talk.
Yeah, is this good like this, or should I increase the volume? Okay, yeah, thank you very much, Banu, for this kind introduction. It's always good to be reminded a little bit about what has happened in one's life. I must admit, I'm much more focused on one day. It's a pleasure to be back here. And yeah, also nice to see Banu again. He was really kind to host me at the Indian Institute of Astrophysics, right, in Bangalore at the time. And I made some important connections there. So, yeah, yeah, thank you for your hospitality. I will speak today not so much about quantum computing, even though there's a connection you will see in a moment, but about a more fundamental physics experiment. And it is maybe where the most impact of quantum information in the end will be, because we're developing all these quantum technologies, and then we have this great control over these systems, and then suddenly we find ourselves doing physics, and you will see here an example of something like this. Yeah, I will start with an introduction about why it might be interesting to test the quantum statistics theorem. And if you don't know yet what it is, you will learn in a moment. And then I will talk about, right, you see here that we're using coherent control of ion strings. So that's something which has been developed for ion trap quantum computing. The new bit is this rotating in there. So these ion strings can actually rotate, and then interesting things might happen. And then I will show data where we actually measure some consequences of the spin statistics theorem. Okay, and then I will conclude. And maybe I figure out which way. Interesting. Did I switch it off? Yeah. This good, right? Let me. This one. Okay. Maybe. Okay. Oh, it's just very slow. Okay. Okay. Let's. Oh. Yeah, we will. Yeah. So this is the group, my research group, and most of them are working in some way on quantum information. Yeah. Okay. The people who are relevant here, or who actually did the work I'm going to present, are who graduated recently, works now at INQ. Ryan and Yulong are still graduate students at the project. Ryan will graduate with this work. Neha Yadav is a postdoc. She came from Bangalore. And Klaus Hornberger and Benjamin Stickler have been instrumental. They're theorists in Germany. They were instrumental actually understanding some of the basics of the system. And then I want to acknowledge, of course, our sponsor. Okay. So the fundamental question I want to ask is, well, this is a picture of two calcium ions. So you take a photograph of two ions. They are separated by 5 micrometers, and you shine laser light on them. They emit light, and then you take a picture. And the question I want to ask are those the same? So in other words, can I make those two ions, which are separated by 5 micron, and because there's a Coulomb repulsion, they can never be at the same location. It's very hard to push them closer than 5 micron. You have to really work very hard to get to 3 micron, and it's nearly impossible to get to less than a micron. So are they the same thing? So that's the fundamental question. And the way this actually question arose is kind of a little bit the following. And you may have heard people running around, especially ion trappers, and say, my qubits are great, they're all the same. And then you should be maybe wondering, is there maybe a problem if they're all the same? And maybe you should be then wondering, are bosons or fermions? One was like, probably, what a stupid question, right? I mean, some of you might be wondering, well, there probably should be fermions because there's spin 1/2, right? Two-level system is a spin 1/2 system. And the point is, it's not a good question. And you will see later kind of why qubits can be both. They can be either bosons or fermions. If I take, let's say, a bosonic ion, or then it's presumably a boson. And if I take a fermionic one, it will be a fermion. But yeah, so there was a question of basically, well, of course, this all has to do with things just being slow. Yeah, okay. Does it matter whether my qubits are bosons or fermions? And we all kind of know that this all has to do with the symmetrization principle. So that a two-body wave function, I have to symmetrize it properly according to whether I have bosons or fermions. And the question, Christian Roos and I, so I was sitting in an office with Christian Roos, who's also now still at Innsbruck, and we're wondering, why do we not have to worry about symmetrizing the wave function of our quantum register? That's what we are wondering about. Why do we not care? But the symmetrization principle, so I come now to the motivation, is of course very pervasive, right? If we want to explain the spectrum of helium, we invoke the Pauli principle. If we look at Bose-Einstein condensation, we basically assume that the wave function has to be symmetric, and then we can explain Bose-Einstein condensation. And if we are looking at, for instance, Hanbury, Brown, and Twiss experiment, we're looking really at two particle interference. And so the question is, why does this physics, is it not relevant for quantum computing? Okay. This field, I mean, the symmetrization really goes to all of science. So you can like find examples in cosmology. We're talking about neutron stars, nuclear physics, atomic physics, structure and stability of nuclei and atoms. In chemistry, of course, the spectra of molecules. And that's maybe something you keep in mind. So basically can keep in mind throughout my presentation, you can think of these two ions I'm going to show you actually as a diatomic molecule. And we have condensed matter, of course, and in quantum optics, we also often study these things. So there's some dedicated precision where people really tried hard to see whether there's a problem. One experiment, which is so simple that it's almost trivial, but maybe that's really a sign of really good science, is where people deep in a mine in, I guess that's Italy. They just send a current through a block of copper. And the idea is to inject constantly new electrons. And if these new electrons haven't been properly anti-symmetrized with the electrons in the copper, what you would expect is that this electron comes into the copper, close to a copper atom, and then falls all the way to the inner shell, because it's not forbidden by the Pauli principle if it's not properly symmetrized, and then you would see an X-ray. So basically, they send current through and they look for X-rays. They haven't found any, otherwise we would have heard about it. And also, like, there was a search by Dima Butcher's group at the time at Berkeley, who actually searched for like forbidden or for two photon transitions which are forbidden because of the symmetrization of the photons. Didn't find anything either. Anyway, what get me kind of, I clicked once, so I'm hopeful that, okay. Yeah. So what kind of, yeah, the question is, can we observe this in this? And what got me intrigued is when I discussed with Christian, I went, and this is maybe a story which may be instructive how to foster interactions. I went to have a glass of water in the kitchen area. And there I met a theorist. The theorist is Andrew Daly, some of you may have heard about, and he is now in the UK somewhere. And I asked Andrew, hey, Andrew, what's a fermion? And Andrew, being a theorist, tells me, well, a fermion is something where if I rotate one fermion around the other, I get a minus sign of the wave function. That's kind of what we learned. I was like, okay. And then he added, well, it's not quite rotating, but it's something similar. Like, and I will explain you what this similar is. But right, it's not that I exchange them. So that's what he meant. What it is, it's actually exchanging the labels in the wave function. And basically, what you do in quantum field theories, the way you construct it, is that you write your two-body wave function, and then you have to tensor two Hilbert spaces together, and you make sure that basically how the wave function is constructed, that it's either anti-symmetric or symmetric with respect to this Hilbert space. But we want to do an experiment. We can't exchange the labels, right? That's not a physical operation. And so what I want to show you now is actually how there's actually a consequence of it. And at the time, I took Andrew literally exchange the particles. So, and let's do this. So basically, here's my wave function of the two ions. So it is a wave function of one ion is left, and I give that a label of 1. And the ion number 2 is on the right side. So that refers to the Hilbert space, and that refers to the location. And then calcium-40 turns out to be a fermion, like even number of protons or neutrons, but odd number of electrons. And then I have to symmetrize the wave function, and then the ion number 2 could be equally well on the left side, and then ion number 1 needs to be on the right side. So that's wave function. And now we're going to look what happens if we physically exchange those ions. So this is what I've done there. So I exchange them. Basically, I put the left ion to the right and the right to the left to the right and the right to the left. And then I end up with this wave function. And if you stare a little bit about on this thing, you realize that this term is equivalent to this, and this term is equivalent to this. And therefore, this is minus psi. So by exchanging the particles, if the wave function had to be symmetrized like this with respect to their labels, by exchanging them in position space, this relative sign here gets basically really ends up in the wave function. So in this instance, I haven't looked further. Exchanging in position space and exchanging the labels is the same thing. So that's a physical representation. Okay, so then the next question is, can we detect this phase here? It's a global phase, so we can't directly measure it. If we just were to measure this wave function, we wouldn't see anything. So we do an interference experiment. And that basically is what Christian and I and later others then came up with. We had many iterations on this. So this all happened actually in 2004 or something like this, 2005. And then this idea was dormant until we actually got more control over iron strings. And then at Berkeley, we realized that we can do the following. So these are my two ions. And I want to point out, this is now a cartoon. This is really a cartoon, and you have to be somewhat careful, but I think it's instructive. So the experiment, what I'm going to talk about essentially goes as follows. We take our two ions. They can relatively freely spin. We will see this in a moment, how we do this. And then I'm coming in with what I call a pi over 2 pulse. And what that pi over 2 pulse is going to do, it will give part of the wave function a kick. It will add angular momentum of, actually, it turns out it will be 4h bar of angular momentum. And then what is going to happen is that part of the wave function starts rotating. So the red part of the wave function starts rotating. And then at the end, I'm going to give it another pi over 2 pulse. And then I will interfere the red and the blue wave functions again. Now, if you are a quantum information person, you say, well, this is qubit number 1 and this is qubit number 2. And then you can see what's happening. I'm going to interfere qubit number 1 with qubit number 2 and qubit number 2 with qubit number 1. And that's, of course, kind of a weird operation. And this is where then all of physics is going to happen. This is an example where we do a pi exchange. So that's the exchange, but you can think, of course, as a 2 pi exchange, and then things are normal and there's maybe not too much special things happening. So that's the plan to do. And now, yeah. So what I found interesting at the time is that there's 2 particle interference, even though the particles never come close to each other. They're always separated by 5 micron. At any point in time during that procedure, I could come in and picture and see that they are separated. So this is what I find particularly interesting. And then you can go to textbooks like Sakurai, who basically make certain remarks. You don't have to worry about the symmetrization principle if the particles are always well separated. And so they're like kind of maybe all some sort of I mean, Sakurai would definitely have understood when I would have told him that experiment, what is going to happen. But I think there's a lot of like intuition, like, oh, the particles have to be somehow close to each other and so forth. But no, it's really, they can be separated and they can be affected. Okay, and if you want to read about it, you can read them. So let's come now to the experimental system. So we're trapping ions in an ion trap, of course. So we apply certain voltages such that we get a potential. We make the potential very rotationally symmetric with these rotationally symmetric electrodes. And then we tune the potential such that there's a relatively strong confinement in this direction and a little bit weaker in this radial direction. And then we end up with a system where the dominant Hamiltonian is just LZ squared over the moment of inertia. And that basically means that it's easily diagonalized and we have angular momentum quantum number squared that gives us the energy. And this is the so-called rotational constant. And this is what I mean. You can think of it as a diatomic molecule. So it's kind of there's a lot of the physics of a diatomic molecule is going to show up here. Right? You have just 2 atoms and they rotate around each other. It's just much bigger. And the rotational constant, so for those of you who know a little bit of molecular physics, they know that this rotational constant is typically like gigahertz, many gigahertz. In our case, it's 10 hertz or something like this. So just 9 orders of magnitude smaller, because it's much bigger. Okay. So this is a picture of the apparatus. Not sure how well you can see it. There's a vacuum chamber, not too dissimilar from what you have here. There are also optical fibers going there to shine in light on these ions. In there is an ion trap. This is a real picture. We played around with a different fabrication method. This is boron doped silicon as a conducting material, so there's no metal in there. And that allowed us a very precise fabrication and very good rotational symmetry, which is key, of course, for this experiment, so that they can easily rotate with each other. Yes. Yes, on top of silicon dioxide. And then we etch down, and it's, I think, 200 micron thick, the boron doped silicon. Yes, the conductivity is enough. And what's really nice is because of the smooth surface, the laser scatter is not visible. It is all specular reflection, which is actually kind of pretty cool. Yeah, no, it works very nice. And turns out it has the same surface noise as metal traps, which is a little bit of a mystery. Why should have silicon? Yeah. Yeah, we trap two ions in there. And of the level scheme for the ions, basically, this is grossly simplified. And this is, we have this S to P transition. This is where we can shine in laser light and collect lots of fluorescence. So these are how we take the pictures. And that key is also this S to D transition. It's a two-photon transition. It's dipole forbidden. And the lifetime of this state is about a second. So that allows us to actually do coherent operations on this transition and to use it essentially as a qubit. And that will be then important for our coherent manipulation in a few minutes, or maybe now, actually. Yeah. Okay, yeah, so the electrode configuration is, this is grounded, the center electrode, this is on radio frequency, and this is grounded again. And these electrodes, we control the asymmetry and actually will, no, that's the DC. Okay, it will be a low frequency AC field. It will be time varying, but like if we want to have a static trap, we will, yeah, for controlling the rotation, yeah. Yes, that was also why we went to this fabrication method, because we want very rotationally symmetric, so we needed to contact it from the back. Basically, we etched from the back through that silicon dioxide substrate, and then evaporated metal from the back. Yeah. And this taught me the difference between a double E graduate student and a physics student. The double E student was able to fabricate this thing in 3 months, and it worked. The physics student, I don't know, would have tried all sorts of these things and it would not have worked. Yeah, yeah, the vacuum chamber is then the next thing. Oh, this here. Oh, yeah. This is a Faraday cage. So it's aluminum, and it is to reduce technical noise. So these ions, they're very sensitive to electric fields, as you can imagine. And it turns out that a lot of the pickup which happens on the trap electrodes is to additional noise. And we could only reliably suppress this by adding a Faraday cage around the apparatus. Otherwise, we are sensitive. Somebody switches on a device somewhere else, and then immediately you have problems. And turned out that actually this was yeah, important. It delayed us 2.5 years until we decided we really need that. And then everything worked. Yeah. Yeah. Good. So one thing I should point out is that we want to rotate these ions, but the energy scales are really unfavorable. I mentioned to you that the rotational constant is only 30 Hertz. oops, rotational constant. So if I, let's say I want to cool the ion string into particulars, cool it to L equals 0. That means that the L equals 1 state 3 Hertz higher, and that's nanokelvin temperatures. It's really cold, and there's the charged particle good, no chance getting there. So the kind of trick is the following. We spin these ions up. So the way what we do is we make the potential very asymmetric, and then we apply AC voltage to this outer electrode and we spin it up. And then we make it symmetric again, and so these ions will spin. And you can now imagine, now you have, let's say, an L quantum number 1,000 or 10,000. And that means if L by 1, the energy changes by actually the rotation frequency, it turns out, by 100 kilohertz, because the Hamiltonian is L squared. So the difference L squared and L plus 1 squared is actually something like 2L. So the faster it rotates, the larger the energy separation. Then I have a much easier time to be cold. So the experiment is conducted in a rotating frame. In particular here in these experiments, I'm going to tell you then later about, so it's about either 100 kilohertz or 300 kilohertz. So think of the whole thing, you're in a rotating frame with 100 kilohertz or 200 kilohertz. These ions are static. So if we have them spinning and then we drive these transition, then we do laser spectroscopy, and then you can see here it spins with 100 kilohertz, and every 100 kilohertz we have now a transition. And this corresponds to the quantum number changing by 1L, one H bar. And so this is how we can do then spectroscopy. Here we have the delta L equals 0 transition, delta L equals 1, 2, 3, 4, and 5. And one can calculate those matrix elements, and actually it turns out that it fits very well at the percent level with our expectations. And yeah, the beam, I should say, we do spectroscopy nearly from the top, but under a small angle so that we have slight projection. Okay, so then the question is, let's say I park my laser here, what dynamics am I gonna see? So I'm preparing the ions, both ions in the S state. I come in with a pulse on the at this 400 kilohertz detuned. And then I can see here some Rabi oscillations. Or maybe you're not convinced yet that those Rabi oscillations, but I see the longer I leave the laser on, I get some excitations, and then I get some oscillations. But here we did only Doppler cooling before we started rotating it into some higher speed. Then what we did is we did first some sideband cooling, where actually we start with a more well-defined state, and then we start rotating, and then we see something which really looks like Rabi oscillations. The contrast is not perfect. To give you some idea, these states here, they have an angular momentum quantum number of on the order of, in this case, 8,000. And there's some uncertainty on the order, let's say 100. So it's fairly well defined. It's not perfect, but it's fairly well defined. And so and based on that, why is this contrast much worse than this? And one way to think about it is, while you're driving these Rabi oscillations here, you are adding additional angular momentum. And then what happens is that whether I'm in the ground state, I haven't absorbed the photon, or I have absorbed the photon, I get some spatial separation of the ions, because I have angular momentum, and then these wave functions separate. So here, for instance, on the fourth order, you start in SS some particular angular momentum number, and then you have added here 4H bar, and then this state evolves faster, and this even rotates faster. And then you can imagine, if these two wave functions don't overlap any longer, I lose coherence. And so, and then I cannot drive Rabi oscillations any longer. And it's a little bit clearer if you look about for a Ramsey experiment, where you really do a pi pulse, you wait some time, another pi over 2 pulse, and in order to make things visible, we actually, and then you can really see if they are separated, the contrast goes to 0. And you can see if you add 1 H bar, you keep the contrast longer. If you add 4 H bar, the contrast vanishes faster because these wave functions start separating faster. But that's exactly what we wanted, right? We wanted to these ions like this, and then we want to rotate them until they interfere again. So you can now imagine you do this experiment, you do this pi over 2 pulse, wait some time, and then you do another pi over 2 pulse, and if they've exchanged by pi, you would hopefully see a revival, and suddenly you would see contrast again. And that's exactly what we are looking for. Yeah. Yeah. Yes. Yes, exactly. Yeah. Yes. Yeah. Yeah, exactly. Yeah, that's the picture. Yes, yeah, yeah, yeah. So there is some substantial uncertainty. So the experiment I'm going to show later, we rotate the 300 kilohertz. L bar is 2000, and the uncertainty is 5 quanta. Including. Yeah, that's kind of preparation. It's not really fluctuation. So the wave packet we generate is, it looks like a Gaussian wave packet, we believe, could be also Lorentzian of that. Yeah, mostly, yeah. There's actually can't distinguish it at yet point, so I don't want to make any claims, but we believe it's a coherent superposition. But yeah, negligible. There is some decoherence going on. That took us a long time to actually understand what's going on there, which actually turns this coherent superposition, of course, in a turns the coherent superposition in a mixture, and then we lose contrast. And then we don't see a revival. And that was exactly the problem. And when we really understood what's happening, so there are some complications. So maybe we can talk about this sometime later, because it probably would take a long time to discuss it in detail. But the short kind of observation is, for a rotating system, T2 can be much, much bigger than T1. So we are kind of so used that T2 can be maximally 2 times T1. This is not true for a rotor, which is interesting and which totally confuses, because we thought that was the case, and we measured a short T2, but T1 was much longer than, T1 was much shorter than T2 by a factor of 100. We measured it, and we were like, what's going on there? And then we are like, oh yeah, it's because the angle, blah, 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 blah. Okay, T1 doesn't really matter. But we were wrong. So, and this has something to do with that the rotor actually has 2 time scales. One time scale is this rotational constant, which determines how fast I can exchange. The other is the actual rotation frequency. And now you can be in different regimes, and depending on which regime you are, different things are. So actually the decoherence properties of these things are fairly, really interesting, much more interesting than that of a qubit because of this. Yeah, but let's maybe, so this is what we were expecting. I've shown you these initial Ramsey fringes, how they decay. We understand that, why they should be decaying. And then there should be a revival after pi exchange. And at 2 pi, of course, things should just return. And here in this pi exchange, you expect a phase, which depends on whether you do the experiments of bosons or fermions. These interference fringes, they are separated by a pi, essentially. So that's the theory. Good. So let's now do this experiment. So pi over 2 pulse, pi over 2 pulse. So we do some state preparation. We do an effective pi over 2 pulse with delta L equals 4.
and then we do a readout. I want to point out that this is really a cartoon. Down here is the wave function really calculated, where basically I have here the ions localized in the horizontal, and then they actually start delocalizing, and then at pi over 4, 2, where basically I have done this, there's some interesting rephasing happening, but then really a proper rephasing is happening after the exchange. So that's the full quantum theory, where we take into account also the angular momentum distribution. Just telling you that this is a little bit more complicated. And what I plot now here is the phase contrast as a function of the Ramsey interrogation time. This corresponds to 2 pi exchange, corresponds to the actual exchange, the pi, what we call a pi exchange. And you can see a substantial contrast here. We can't make any statements about the phase because we haven't calibrated it properly. So I don't show here the phase. But the point is that we have some contrast here, we have some contrast here, here and here. The contrast is nearly 0, and here there's a revival. So that's proof that you can interfere 2 ions which are distant with each other. So that's basically the main conclusion from this experiment. And now if we had really control over the phase, we could tell whether the boson or fermion, but there are many, many different phase contributions, so we haven't been able to separate that out. So when you see, so this was a little bit, maybe a little bit of a surprise to me, because my game plan was to see this, and then to go and see first that we can see the 2 pi, and then to make sure that the ions are really indistinguishable, and to see this. But the graph, in the lab, they said, well, Hartmut, it's really hard to see this here because you have to have twice as long coherence. And they just went for this first. Until they got this, then they optimized things, and then they were able to see this. And then, okay, maybe we did a mistake in our calculation by a factor of 2. Maybe that's the 2 pi exchange. And then we're like, okay, can we destroy this interference between the 2 ions? Right? They are different ions, and you should think it should be easy to make them distinguishable. Right? That was our thought. It turned out it was actually not so easy. So it was very hard to destroy this interference without destroying that interference. So that was a little bit, for me, the learning experience where I thought that this is the difficult part, to make the ions indistinguishable. And it turned out that it was actually hard to make them distinguishable. And in hindsight, it is obvious because these ions are in the same trap. Our laser light shines on both ions. In order to make them distinguishable, we need to do something to one ion, but not to the other. But these 2 ions, they're rotating with 300 kilohertz. Whenever I shine in the laser light, ions, and within 3 microseconds, they have swapped already position. So it's very hard to do something individually to the ions. But he came up with a way, and I want to talk about this now. So yeah, this was this question: can we make the ions somehow distinguishable, to really learn a little bit about what is going on there? The first is using the electronic states to mark the ions, to tell this is ion number 1 and ion number 2. In our case, leads to a trivial loss of coherence, so it's not really. We are doing now, hopefully soon, experiments where this will be possible. But because the way our interferometer is constructed, we're using essentially entanglement between the rotational degree of freedom and the electronic states. And if you do something to the electronic states, right, that's leads then to a trivial loss of coherence. Manipulating the center of mass degree of freedom. So we have this ion, and it has 6 degrees of motional degrees of freedom. So I have my 2 ions. They can oscillate like this, up and down, back and forth. Those are the center of mass modes. But then we have also the relative motions. But working on the center of mass modes is not going to help us, because that's common to both ions. Whatever I do affects both ions the same way. It's not going to do something. So that leaves actually 2 modes left. there's the rotation, there's this mode, but that turns into the rotation. So that is part of the interferometer. We can't touch that, but we can do something to the stretch mode, this and this. Now you maybe know, if you look at the wave function of a harmonic oscillator, if you're in the 0 state versus the 1 state, the symmetry of the wave function is changing, right? So it goes from a Gaussian to something which looks like this. When I do now a reflection, I get a minus sign of the wave function. So that's the idea. Yeah. So, but before going to that, let me look at the total wave function. It's going to be a product of, it's going to be a product of the electronic and the motional degree of freedom. The motional degree of freedom will have degrees of freedom. This is where our interferometer takes place. So we are now basically looking at the symmetry of these modes, because right, the symmetrization principle tells us this wave function needs to be symmetrized. And by changing the symmetry of one of those, I'm going to change the symmetry of these guys, or the product of these guys needs them to change, because the electronic state starts in the SS state. That's always even. So we are going to essentially control the symmetry of this rotational degree of freedom by changing the symmetry of those. The experiments I showed you actually turned out I needed to cool, or we need to cool the stretch and this vertical rocking mode into the motional ground state. But the point I want to make is, if we have defined the symmetry of all those modes, except the rotel, that defines then the symmetry of the rotational degree of freedom. And that's a sum over all this angular momenta. And basically what it means, we have either even or angular momenta, depending on what these other modes do. And that's basically the physics we are looking at. And you know all of this from molecular physics. Or maybe that's where it shows up. Same way. So kind of this is really a pictorial representation of the experiments we do. So here we have an L bar of roughly 4,000. And then you can see here, this is really how wide our angular momentum distribution in these experiments are. Here we have, actually you don't know which is even or odd, but you can see they have both the same expectation value. Yeah, okay, so if this is really 4,400, this needs to be even and that needs to be odd. And that actually leads to the different phase we have after the rotation. Yeah, so we have modes, the vertical rocking and the stretch mode. It turns out if I change the symmetry of the stretch mode wave function, the symmetry of the two-body wave function is not changing. And that's because the stretch mode is a symmetric mode. The ions move like this. If this ion moves to the right, this also moves away from the center. And if I basically change the symmetry of nothing is happening, in cylindrical coordinates, you would say that rho goes to rho, the radius goes to the radius. But here, this mode actually, something is happening, because Z goes then to minus C under this reflection. And then basically the symmetry, whether the wave function is a Gaussian or is this wiggle actually makes a difference, and actually the wave function changes the symmetry. So yeah, we did this experiment. So first here with the odd angular momentum, calcium is a fermion. All other modes are even, and then therefore the rotational needs to be odd. And we see this Ramsey contrast here, okay? And if we prepare the ion string with the vertical stretch mode in the 1 state, in the Fox state, where actually we need now, and it turned out that was another mistake, we need now to do single ion addressing, and that's the distinguishing. So we did single ion addressing, and then we were able to prepare the Fox state n equals 1 of the vertical stretch mode, and you can see that the interference fringe is now shifted. how much we expect? You expect pi. If you look at this, you see it's not quite pi. Turns out, well, we were expecting 180 degrees. After some thinking, we expected 160 degrees. And the reason is because if I excite this mode, the ions ever so slightly move closer to each other because the Coulomb interaction, they move like this, slightly closer to each other. That changes the moment of inertia, and that changes when the interference contrast happens, and that shifts the phase. So after calculating this to be 20 degrees, we expected 160, but we measure 135. We are not sure what's happening here. I want to point out that also this experiment is sensitive to Aharonov-Bohm effect. And so there may be something like this, and we need to really sort out what's there. But I think that's part of the physics, and that's interesting. So that's what we are going to do maybe the next year or so. Yeah, we can now basically go to this experiment. What we were really trying to do is to remove the contrast after a pi exchange. And we basically do this by creating a superposition of 0 plus 1 in this mode. And then the sinusoid and the cosine interfere with each other, and it leaves a flat line, basically removes the contrast. That's the picture, because I have odd and even angular momenta. And if I initialize it in a Fock state of the vertical, we have the contrast. So that's now able to basically make the ions distinguishable. Where we have it in a superposition, you can now think about it, right? Having a superposition of doing this and not doing this, and that is distinguished than left and right. Yeah. And for a 2 pi rotation, you can see that the two that basically we have contrast again. That's proof that we're really looking at the pi exchange here. Okay, so I want to conclude. What I want to say is that qubits that always stay remote from each other may become indistinguishable if you work really hard. So if you do such an interference experiment as we did, and then you actually worry whether you have bosons or fermions, or whether you have identical qubits in the first place. Well, from the physics point of view, this is a controlled symmetry test. So in contrast to many other systems, we have a good control over the various symmetries. The entities are really well separated. This is different from a molecule. If I think about molecular physics, and I have two atoms, and they share an electron, those are not really different entities, whereas our ions, they are far separated. I can manipulate them individually. So that allows us a much better test of things. It's also the physics is a very different length scale and energy scale. And we also control over the rotation degree of freedom and so forth. So actually, we are able to see centrifugal distortion and many other things which are very hard to observe in molecules. So it's kind of an example of we're looking at a new physical system, and therefore we can look for new physics or physics from a different angle. So this is maybe one of the takeaway messages. And then in the future, well, we have this unexpected phase accumulation we really want to understand. We believe it may have something to do with the centrifugal distortion. As the ion crystal rotates, there are centrifugal forces. There's a quantum Coriolis force, so to speak, you may call it. There's an Aharonov-Bohm phase and so forth. Another kind of open thing is we needed to cool the horizontal stretch mode. We didn't expect that, so we want to understand that also, why the contrast gets worse. And I'm kind of curious whether this is a novel system, whether it probes some kind of unusual interactions. And when I say unusual interactions, maybe that's synonymous for dark matter. Is there either some dark matter models we are actually testing now? That's a question I would love to discuss with a theorist who works on dark matter. Yeah, next steps. I want to measure the absolute phase, calcium-40, a fermion. can also think about loading calcium-43, which should be a boson. What we're working on at the moment, though, is these decoherence models. So we have seen this interesting decoherence properties. So we want to work on this a little bit more. And then we can think about you going to 3 or maybe even more ions. And one can actually think about going towards macroscopic rotors. So I could imagine putting a carbon nanotube in such a trap and have that spin. And then suddenly you could test whether the carbon nanotube is really symmetric. So it could be a cool way to verify materials properties or a quality control of materials. So because even a single defect in a carbon nanotube would not make it symmetric, and then you could actually detect that. So maybe in 100 years, somebody cares about this. Okay, yeah, this is a picture of our 3-ion crystal we loaded where we doing also experiments. And yeah, that's it. Thank you for your attention, and I'm here for questions.
Yeah, sorry. So how critical is it to finally, say, for example, anti-symmetrize a 2-qubit register in practice?
As long as you're not getting crazy with like where you exchange them and you don't know whether, so the whole point is that you do an experiment where you exchange them, but you don't know whether you exchange them, right? So this is this, as long as you don't do that, it's it's not relevant. This morning, when I started thinking about this talk again, it occurred to me, let's say you want to do some quantum simulation of a quantum system where you have fermions. If you do that with qubits, you have to work probably hard to somehow encode the symmetrization of the wave function. But if you are maybe using really fermions, and if you are clever about how you use them, you can use this effect, and maybe this will reduce the number of resources. So I know that there is, and I didn't have the time to read, there is a paper where people think about this idea using neutral atoms, where they basically use the fact or want to use the fact that they are fermions. But maybe this is a different way, and maybe it has some advantage. So this is what I was thinking this morning, that there could be some shortcut. But I can tell you, the experimental effort we go here through is substantial. It's not a trivial extension of the ion trap quantum computer. That's what I want to say, right? You have to really spin it up to get the energy scales high enough. So, well, let's say you have a 2D array. I could imagine these junctions in the center of the junctions to spin the ion string up to do that experiment, and then yeah, maybe it's not so stupid. Maybe one really should think about this. Yeah, maybe it's. I was just thinking. So this was a difficult experiment, I should say, right? So we started thinking about it 2005. We started going after it in 2016. Now we have 2026. But the addition is really, I need to have a symmetric trap. So maybe the junction is good enough. And then if you have enough electrodes there, one could potentially think about that. Basically moving 2 ions into that junction, spinning them up and making them indistinguishable, and then separating them again. So maybe, yeah.
Yeah, but I have another question. I don't know if you already told it and I missed it. But when you spin these 2 ions and then you want to, say, for example, scale it up in the future, won't the heat actually start, because there is this rate of change of acceleration that then starts adding to the error budget, right? In whatever you want to see as your signal, or am I overthinking it?
Oh, so as we accelerate them so that's only the state preparation, and we do this what's nearly adiabatic. So we, okay. Maybe I should wash my dirty laundry somewhere else, but we do not understand the spin-up process. In a sense, we ramp it up in 50 microseconds, and if we ramp it up with 51 microseconds, it's not working. If we ramp it up with 49, it's not working, but with 50, it's working. We come in the next day, and the next day, it works at 55, but not at 54. But then it's stable, so we do not really understand this. Things have gotten much better when we made the trap stiffer. We have a much larger range where it now works every day with those parameters, but like in the first. And so something is happening during the spin-up process we do not really understand. And then we also, right, once we have spun it up, we need to make the potential symmetric, and we ramp it down adiabatically. And we do that. That was, yeah, about hundreds of microseconds. And that determines how close you can actually go to pure angular momentum state. We believe that after the spin-up, we should be able to have really a well-defined coherent wave packet with well-defined angular momentum. And if that angular momentum maps then onto the perfectly on the free angular momentum, you would expect a pure angular momentum eigenstate. And you have to ramp down slowly enough. You have to adiabatically transform from this wave packet with well-defined angular momentum to a free wave packet with well-defined angular momentum, where now, right, the pure angular momentum doesn't have any orientation. So that's that adiabatic mapping. And so at the moment we use a millisecond. If we maybe use 10 milliseconds or so, we could get narrower, but we haven't investigated all of these things because it turns out that they are not that important for us. But what's important for us is that the angular momentum distribution is narrow enough that we can get good coherent operations. And I've shown you how the Rabi oscillations are 95%. That's good enough for us.
Thanks.
I hope that answers a little bit your question.
Yeah, definitely. Yeah.
Yeah, the question.
Yeah, probably that's probably that is the gist of it. Yeah. Yeah. Well, I mean, I've shown you an experiment where I've shown you that you need to treat the two ions as indistinguishable particles. So this experiment here really like proved to you that these two qubits we had at the beginning, I cannot treat as distinguishable qubits. So in that sense, I've made them indistinguishable. If you don't do this exchange, you don't have to do that, right? And then you can label your qubits as 1, 2, 3, and everything is fine, and you have your lines in your quantum algorithm, and all the quantum information people are happy. But if you do an experiment like this, this picture is wrong. It's just, you cannot say this is ion number 1 and ion number 2. It's just wrong, right? You cannot interfere then qubit number 1 with qubit number 2. It's a non-operation, but I've shown you that there is contrast. So it is a sensible operation here. And the resolution is that you need to symmetrize your quantum register. Then everything makes sense. And the whole math basically describes really what's happening. So in that sense, I believe in order to make them indistinguishable, you need to do an experiment like this. You need to, in your quantum algorithm, you would need to embed something done here. And then you would make them indistinguishable. I kind of doubt it, but because we don't understand it, I cannot say that you are not right, right? I personally, I believe it has something to do with that it's not a stiff rotor. Ions basically, while they move, if they move a little bit, essentially what happens is that the equilibrium position is slightly further away, and that these corrections we haven't properly taken into account. That's what I think, but it's not proof that you are wrong, right? That it could well be that there is a problem to begin with. Could well be. I don't want to exclude it because we don't understand fully what's going on. I think we have a good understanding of the basics, but not really all the details. We are missing something.
We used as a consumable resource like entanglement in quantum communication task for security.
Yeah, I think that comes back to a little bit this idea of maybe it's a more efficient way to encode indistinguishable fermions. Because if you want to calculate a system where you want to simulate the physics of fermions, the wave function needs to be anti-symmetrized or symmetry. Okay, fermions anti-symmetrized. And so I do not know what the algorithmic overhead is to actually encode that. Maybe a question for Banu. Or some of you who are working on this. And that overhead you could save by actually doing like this. Or maybe to put it maybe a little bit more trivially, if you wanted to simulate the physics of a diatomic molecule, you could use tons of qubits and do some computation, or you can build the system and then observe the physics directly there, right? So I think a little bit the trick to find a system which already does most of the interesting dynamics you want to, let's say you want to do a quantum algorithm, a quantum simulation, or whatever you want to call it, of a particular physical system. If you can find a physical system which naturally does already most of what this physics system you want to simulate is doing, if it does naturally already most of this, it's great. You have to do much less work. I mean, let's say this is a really trivial example. Understand the physics of a leaf. Well, take a leaf and study the leaf, right? Don't put it on a quantum computer. But why do we put it still on a quantum computer? Why would it be great to put it on a quantum computer? Because I can ask many more questions, because I now can look into the leaf. I can do state tomography. I can change the things. Here, with such a system, if I want to study the physics of a diatomic molecule, if I take an artificial diatomic molecule, I can reproduce the phenomenology, but I can also change properties of that molecule. And that allows me then to learn things. So in that sense, this kind of, if you can now inherently make your qubits fermionic or bosonic, you may actually have a win situation, because now your quantum register does naturally already take care of the symmetrization. I don't have to do it in algorithm any longer. Therefore, I need fewer qubits. And I still have to control. I still can go in and measure certain things. But of course, then I don't have the freedom to do something mean to the symmetrization and to turn my fermions into anyons, for instance. This is not possible now any longer. So I'm losing then a little bit. But overall, it might be a win. So that's maybe the point I to make here.
I think this distinguishability thing or indistinguishability thing per se. So the security of quantum networks or quantum communication tasks, they depend on this kind of indistinguishability, right?
It maybe in some instances, I'm not sure whether that's in general true. So
I was whether this indistinguishability thing can be used as a consumable resource, just like
yeah.
entanglement.
Yeah. So what can be done is that this indistinguishability, I think, can be transferred into entanglement. You can use it, I believe, to entangle in certain protocols. That's one thing. What we discussed actually yesterday was using indistinguishability as an interferometric interferometers to actually, yeah, let's say if you have two indistinguishable particles, you let one interact with the environment. Then if the environment learns anything about that part, or that particle learns anything about the environment, it will be made distinguishable, and then you lose indistinguishability. So that was what we discussed yesterday, and that would be. Yeah. Yes and no. The problem a little bit is that we have this iron ring spinning, and then if you put something there, whatever you put there will interact with both on average the same way. So it's not, yeah. So you would have to have that thing also orbiting this thing. Yeah, gets challenging.
Stretching mode to make it distinguishable. But then you said this stretching mode is say symmetric, right?
Yeah.
But then how can you discard the effect of the common mode, which is asymmetric from the?
Okay, that affects both ions the same.
Right.
The same.
Mm-hmm.
And so then.
From the.
So if I change the ions, it will be still the same motion. Let's put it that way.
Mm-hmm.
If I change, it will be still the same motion. So if let's say I move right, and I exchange them, both still move right. For the stretch mode, if both move outwards and I've exchanged them, both will still move outwards. If I have the vertical rocking mode, if one moves up, the other moves down, and I exchange them, now something else is happening. So let's say they move, let's say this side, which is for you, for me, it's the right side, for you, it's the left side, moves up, there's a change in there, and now the other side moves up. So that's why the vertical stretch mode is still.
Okay. Yeah, thank you.
So it's like two things need to come together here. The harmonic oscillator wave function needs to geometry, and the motion itself needs. So that is took us just 5 years to understand this. So.
Thank you.
But it was not our main focus, but basically initially we thought, yeah, we can use the stretch mode, and then at some point the graduate student came like, no.
In your case, in your experiment, these two ions overlap. I mean, your function or associated to two ions, they don't overlap, right?
Yes.
And then still they are indistinguishable.
Yes.
So I mean, in physics, I mean, for example, if you consider QFT, quantum field theory, then probably you can explain that this is just a, field, and they're just two excitations.
Yes.
Otherwise, I mean, it's very hard to actually digest that two particles are kind of not overlapping. Still, you see the. I mean, this.
Yeah. You summarize exactly the motivation I have for this experiment. Yeah. This is why I wrote to Banu, where, okay, we have these experiments and they show that you may need to describe your qubits with quantum field theory. Exactly, because that's exactly the right description. There is only a calcium-40 creation operator, an annihilation operator. and there's no ions itself. And comes back actually to my PhD defense, where a theorist asked, I work with a single ion, and the theorist said, "What do you mean with a single ion? There is one carbon 5+ ion." I didn't understand what he meant, but it was really this idea, what you're just paraphrasing. There is only one electron, and you can have electron excitation, right? There's only the electron field, and you can excite it in particular ways, but that's it. There are not multiple electrons. There's only one electron, and all electrons are the same thing. And it's something, I've heard it so often, I've seen experiments, but I haven't accepted it yet, but maybe I will at some point. Thank you.
Any other questions? So if not, let's thank